Can folks in the chat hear me okay? Wonderful, thanks. Okay, so as usual, remember to do the seating survey. In case you missed it, because I am moving this week's content videos and homework to next week, if you wanted an extension on last week's homework until the end of today, just let me know, and I'm happy to do that. I do not quite yet have figured out when, what exactly is getting dropped in later weeks, so I haven't officially moved the Friday homework. It will get moved, but I only want to move it once, so I will do that very shortly. Tomorrow at 5, exam number 2 is going to be released. It will be due Sunday at 5. There is a post on Piazza about what we know so far on the exam. We're looking at 3 parts to it. The first part is going to be kinetic analyses of simulated experimental data, where you will be doing either the method of initial rates or the method of flooding in order to find a rate law. I have put up a practice spreadsheet that you should spend some time on getting used to and watching the video on how to navigate Excel particularly well with respect to these particular calculations you'll be doing. There is the second part is going to be on kinetic mechanisms and transition state theory. 2 weeks ago, roughly, we did an extensive example in class with a couple of different mechanisms for the same overall reaction, and we analyzed how those 2 different mechanisms predict rate laws that we would be able to distinguish so that we would be able to identify which mechanism is more likely to be correct. And then the third part is on equilibria, and really there are only 2 topics we have for that. There's Le Chatelier's principle, and then there is ice tables for calculations, and Le Chatelier is, I'm sorry, ice tables really is just a quantification of Le Chatelier's principle in many ways. So they all kind of fit together on that. So that's how the exam is going to be structured. We're not doing a whole systems kind of thing for this particular exam, simply because there's enough to wrap your head around with the spreadsheet simulations that you'll be doing. So the other parts of this will not be focused on individual systems the same way that the first exam was. Any logistical questions anybody has before we get into some content? Okay, so there were really only 2 questions on Piazza that were brought up. One of them was going back to kinetics. The other one is on equilibria. The kinetics question was trying to get a better understanding of what does it really mean for a reaction to be 0th, 1st, or 2nd order, and then how do you determine it mathematically or otherwise. So I'm going to do a quick overview of these ideas. The order comes from the rate law. So if you have a rate law, whatever the exponent is here is the order. And so if this exponent is 0, then it is 0th order. If this exponent is 1, it is 1st order. If this exponent is 2, it is 2nd order. Now, you do have to make sure that you are paying attention to whether you have something like this, where it is 1st order in each of A and B, but 2nd order overall, because there are two species that are having to run into each other for this reaction to happen. When we talk about ways to determine 0th, 1st, or 2nd order graphically, it only works in cases where there's a single component that is varying with time. The graphical approaches don't work in cases like this. So, but if you are in this case here, where there's only a single component varying with time, then the easiest way to determine your reaction order, 0th, 1st, or 2nd order, is by looking at three different plots. The first plot is just straight concentration versus time. The second plot is the natural log of concentration versus time. And the third plot is 1 over concentration versus time. One of these three, if it is zeroth, first, or second order, one of these three will be linear and the other two will not. This is the case where for zeroth order, if this one is linear, it is zeroth. If this one is linear, it is first order. If this one is linear, it is second order. Again, remember though, this only works if there is only a single species whose concentration is changing over the course of the reaction. If you are dealing with a more complicated rate loss, such as this one here, or if you're dealing with something like fractional orders, half orders, or something of that sort, or even negative orders, then you need to use a different method to determine the rate law and determine the reaction order. And the two methods we have talked about in this class are the method of initial rates and the method of flooding. So I go through examples of doing both of these methods in the context of the practice spreadsheet in the tutorial video that I put together. So I do recommend going and taking a look at those for that. And so that's the overview of reaction order and the different methods that are used to determine the reaction orders. Any clarifying questions on any of that? Okay. All right, the second muddiest point we had was how do you know if the reaction shifts left or right? So the general idea of this is comparing Q and K. Both Q and K have the same structure. They are products over reactants, where the exponents of the individual products and reactants are the stoichiometric coefficients of the species in the reaction. The only difference between Q and K is that K is that set of concentrations in this form when the reaction has reached equilibrium. Q is the same thing at any time, whether it's reached equilibrium or not. So if you look at Q and it happens to equal K, then you know you are at equilibrium. If you look at Q and Q is greater than K, then thinking about this structure right here for both of them, that means that the numerator is too big, right? So in order for Q to become K, to approach equilibrium, some of the numerator has to turn into some of the denominator, meaning that products turns into reactants, and so the reaction shifts to the left. If Q is less than K, then that means that the numerator is too small. You don't have enough products. So the reaction will shift from denominator to numerator in order to bring Q up to K, and so the reaction will shift to the right. That's the basic concept of which way will the reaction shift. Now, this concept can be applied in a lot of different situations. So for example, you can look at an ice table and you look at your initial concentrations of things. So let's suppose that our equilibrium marker is here so that we have A plus B goes to C or something like that. Now, if you look at this and you find that you have some kind of initial concentrations for A and B, but you have a 0 concentration for C, well, if there is no C, then the reaction has to shift to the right because you can't have it shift to the left because you'd end up with a negative concentration, which is a non-physical concept. Okay. Now let's think about what that means in terms of this idea of Q versus K. If C, our only product, is 0, what's the value of our Q? Because products are in the numerator, our value for Q is going to be 0, which will be smaller than any value of K you could possibly have. So Q is less than K, so Q has to shift getting larger, meaning you get more products. Okay. Let's suppose you're starting with a situation where you've got some of everything. So 0.1, 0.2, 0.1, which way is it going to shift? At that point, you might look at the equilibrium constant. So if you look at the K and you see this is some number like 10 to the 12th, some very, very big number, then the fact that you have sort of middle numbers that are about the same on the left and the right means that our Q, our initial condition, is going to be somewhere around 1. K is bigger than that, so the reaction is going to have to shift to the right in order to bring Q up to K. If, on the other hand, your K is really small, like 10 to the negative 12th, then the opposite argument works and the reaction shifts to the left. When you are doing your ICE tables, if you look at your equilibrium constant and it is either very large or very small, it is usually a good idea to pre-shift the equilibrium in the direction that you think it is going to go so that you are starting closer to equilibrium in the first place. So this is probably the most complicated portion of an ICE table, so why don't we go through an example of looking at that. So let us suppose that we have a K that is 10 to the negative 8th, and our reaction is A plus 2B is in equilibrium with 3C plus D. Okay. So we have our initial conditions. We're going to have a shifted initial conditions. We're going to have a change and an equilibrium. Okay. And so let us suppose that we are told that we are starting with 0.1 molar in everything. Okay. So our K here is extremely small, which means that equilibrium is going to be where? Closer to reactants or closer to products? Closer to reactants, that's right. Because remember that Q's and K's are products over reactants, so if our K is extremely small, that means you have a small numerator and a large denominator, okay? All right, so that means that we want to shift this reaction as far towards reactants as possible. So if we look at the reaction stoichiometry here, which species are of the products, when they react away to make reactants, which of them are we going to run out of first? C, right, because we need to use 3 times as much of it as we do here. So C is the one that we're going to take to 0. So we're going to shift it by subtracting off 0.1 of this. So this is going to go to 0. Which means that we're going to lose 1/3 of that from D. So we are shifting it that way by 0.1 of the C, which means that the D is going to shift by 0.33. So this is going to become 0.67. This one is going to go up by, not 0.33, 0.033, excuse me. So 0.067, right. This one's going to go up by 0.066, 0.067, because it's going up by, oh, yes, it's going up by 2/3 of the 0.1 that we shifted. So this is going to become 0.167. And this one is going to go up by the 0.033. So this is going to become 0.133. So what we have done is we have said our shifted initial condition is going to be as far to the left as possible. So there's a question on the chat. Can you explain why we use C again, or why you wouldn't use D? So if we used D as how much we were removing, we would have to remove 3 times as much C, and we would end up with negative 0.2 for the concentration, which is non-physical. So you have to use the one that runs out first. Okay. So we think now that we are probably pretty close to equilibrium. It's not going to be exactly at equilibrium because we've overshot by a little bit, but hopefully only a little bit. So at this point now we can ignore the top line. My black pen is running out. We will switch to green. But now we ask, from our shifted initial position, as it approaches equilibrium, which direction will it shift then? It's going to have to go back towards reactants because this one's 0. I'm sorry, I said reactants. It's going to have to go back towards products because this one is 0. So again, we use our stoichiometric coefficients. So this is going to go up by 3x. This is going to go up by x. This will go down by 2x. This will go down by x. And we have 0.133 minus x, 0.167 minus 2x, 3x, 0.067 plus x. Okay. How did you get 0.133 and 0.167 again? So this was taking our initial amount and adding to it the amount of the reaction that we shifted over by. So if we shifted over by 0.033, here we shift over by twice that much because because it's 2b. So we take 0.1 plus 0.033 times 2. Here we take the 0.1 plus the 0.033 times 1. Why are the reactants negative if we're shifting left? We shifted left to go from here to here, but we overshot by a little bit, and so we're shifting back to the right by that little bit that we need to. Just to confirm, if D is 1/3 of C, the amount of D that was used up is 1/3 of C. So we are subtracting 1/3 of C from the 0.1 for the D. And I don't understand the question. Just to confirm, what would the x's look like if we didn't have to shift back? The point is that because we went as far to the left as possible, you have to shift back. And that was the entire goal, was to get it so that we have one of them at 0. Okay, now at this point, we can tell that our equilibrium expression is going to be somewhat nasty. So you need to get yourself very used to writing down an equilibrium expression. This should be extremely quick. So to show you what we're doing, we know it's products over reactants raised to the powers of the stoichiometric coefficients. So you should be able to write down very quickly C cubed D over AB squared. Okay. So that is the expression we would be plugging these values into. And we can see here that we'd end up with a 3rd order polynomial because this gets cubed right here. But our goal was to be very close to equilibrium already by the shifted initial line. So what we're going to do is assume that our x is small compared to 0.067, that our 2x is small compared to 0.167, and our x is small compared to 0.133. So then we ignore that part, ignore that part, ignore that part. This one we don't have anything to compare to, so our x stays in place right here. So if that assumption is right, we can take our 10 to the minus 8th and then plug in the values here, neglecting the x's where I've marked them out. So we have 3x, the quantity cubed, times 0.067 over our a, which is 0.133, times 0.167, the quantity squared. And so at this point, it's just a matter of plugging it into our calculator to find the value of that, the value for x. So x squared is going to be 10 to the minus 8th times 0.133 times 0.167 squared divided by 0.067 and divided by 3 squared, which is 9. And so then x is going to be the square root of this. And because I'm just making numbers up here, I don't know how good this is going to end up being, but let's take a look. So 1e8, nope, that didn't work, did it? Change sign. 1. There we go. Times 0.133 times 0.167 times 0.167 divided by 0.067 divided by 9, and then we take the square root of that. And we get that x equals, let's do 7.8 times 10 to the minus 1, 2, 3, 4, 5, 6, 10 to the minus 6. And we see that indeed x is small compared to these three things that we were looking at. So this ended up being a good approximation. Yes?
Would 3x be squared or cubed?
The 3x, that should be cubed. You're absolutely correct. So thank you very much for that. This is cubed. So this is going to be 27, and this is cubed. And so then this is going to be the cube root. So let's try that again. Thank you for keeping me honest. 8, change sign, is that. Times 0.133 times 0.167 times 0.167 divided by 0.067 divided by 27 and the cube root. Did I do that? That can't be right. I think I hit cubed instead of cube root. Yes, there we go, that's better. So 2.7 times 10 to the minus 1, 2, 3, 4, 10 to the minus 4. And so it's closer to a situation where we might have to take it into account, but it's still far enough away that we're okay with this approximation. So that is essentially as complicated as an ICE table is going to get for this, this exam. Okay. Yes, Ashlyn's right that it should be cubed. 9 instead of 27. And yeah, it should have been x cubed. Right, okay. Yes?
Is there always going to be a case that we assume that the x's are going to be smaller
So the reason we were able to make that assumption was by looking at the equilibrium constant and saying that the equilibrium is going to be very, very close to entirely reactants. Okay? And so that's why we did the initial shift to get it there, which meant that the correction that's going to happen will be small because we're starting very close to where we think equilibrium is going to be. Okay? So if this K had been 10, rather than 10 to the minus 8th, we would not have been able to make that approximation. And we would have had to have gone on and solved the nasty polynomial that, that we were dealing with down here. Yes?
So could we have solved with those and like still got her answer?
Yes. Yes. So for the chat, the question was, could we have gone ahead and solved the nasty polynomial anyway? And the answer is yes. And I would recommend, if it's anything other than, anything above a quadratic, that instead of trying to look up the formulas for a third order polynomial or a fourth order polynomial or something, take it over to Wolfram Alpha and have it do the solution for you. Okay. But where did the x cubed come from? Okay, so the idea here is that we started with this expression here. I factored out 3 cubed so that that became the 27. And so the x cubed is right here. I just solved everything by moving it to the other side. And I swapped sides so that we would have it like this. So, okay, so you got that? Good. Okay. Could we have done the same assumption if k was huge but going the other way? Yes, absolutely. So, and in fact, the example in the ICE table video, the very last example, is exactly that. It is a case where we have an enormous k, and so we assumed that the reaction, we shifted our initial conditions all the way to the right instead of all the way to the left. Okay. Any clarifications or further questions about ICE tables and this kind of calculation? Okay, so that's all of the muddiest points that I got off of Piazza, so I am happy to talk about absolutely anything. For new topics, can we do a kinetics mechanism example again? Sure, we can do a kinetics mechanism. So, let's see. It's always tough to come up with one because I don't know if the one I'm going to come up with is going to be easily solvable or not. So let's suppose, I tend to do the I tend to do the steady state approximation, so maybe I'll give you one that now that's doing a pre-equilibrium approximation. Let's suppose we have A plus A goes to B, and we'll have this as an equilibrium. So K1, K minus 1. Let's do then B plus A is an equilibrium with C. So basically this becomes A2 and this becomes A3. Why don't I actually write it that way because it'll be a little clearer. A2, make this A3, whatever that is. And then once we have A3, so K2, K minus 2. And then we'll have A3 plus B goes in a non-irreversible step to, we'll say, 2A plus C, our product. Sure, we can do that. Okay, so in addition to being given what the various steps are, you would have to be told some further information about what kinds of approximations to use. So in this case, we are going to say that the final step here is the rate limiting step. And we're going to say that we should use the pre-equilibrium approximation for the first two reversible steps. So the first thing that I would do, that I would recommend doing, is to write down the rate laws for each individual step. And just like I was saying that writing down the equilibrium constant expression needs to become second nature, needs to become very quick to do. The same thing is true for writing down the rate laws for elementary steps. So R1, which is going to be the forward reaction here, it is always the rate coefficient times the concentrations of the reactants raised to their stoichiometric coefficient. So in this case, it's this could be written either like this or as 2A. And so we can write the forward rate as K1 concentration of A squared. So why don't we right now have you guys spend a moment practicing that to write down R-1, R2, R-2, and R3 for each of the individual steps. I'll give you a couple minutes to do that. Okay, so check your work. All right. Okay. Yes.
So we don't have to do R-3 because that's the rate determinant step.
So when providing this mechanism, the fact that I didn't provide a reverse arrow for it is indicating that that reverse reaction is too slow to be meaningful. And so we act as though it doesn't exist. Okay, so question from Ashland, can we go over these, just to, these right here? So what we are doing is we are taking the rate coefficient for each step, and all we do is we put the reactants for that step. So the R-1 step starts with an A2 molecule and goes back to 2 A's. So the reactant for the reverse reaction is a single A2 molecule. So that's why we have this to the first power, because there's only one of them, and that's the rate coefficient. It's that same pattern for all of them. This forward reaction is K2 times the concentration of A2 times the concentration of A. The reverse reaction is the K-2 times the concentration of the only reactant for that step, the A3. All right, so the pre-equilibrium approximation says that when you have an equilibrium, the forward rate equals the reverse rate. So we would write that as R1 equals R minus 1, and R2 equals R minus 2. So what that will look like is, let's start with the R2 case. K2 concentration A2 concentration of A equals K minus 2 concentration A3. Now, and then from the R1 step, we have K1 concentration A squared is going to equal K minus 1 concentration of A2. And since we're told that this is the rate determining step, we know that our overall rate equals R3. It's K3 concentration A3 concentration of B. Now, what is the problem that we need to fix in this rate law? Why can't we just stop at this and not have to deal with the pre-equilibrium approximation? That's right, from the chat. A3 is an intermediate. Do we have any other intermediates in this reaction, in this mechanism? A2, yes. A question, why is it an intermediate? Well, if we look at the overall reaction, we have AAA, so 3A plus A2 plus A3 plus B yields 2A plus A2 plus A3 plus C. The 2A cancels with 2 of the 3A's there. The A2 cancels and the A3 cancels, and we're left with A plus B goes to C. Oops, I'm off the bottom of the screen. Sorry about that. There we go. So I took everything on the left, took everything on the right, wrote it down, canceled out the things that are on both sides, and we end up with A plus B goes to C. And so we see that in this mechanism, in the overall reaction, there is no A2 and A3. They are created by steps and then destroyed by those steps later. Okay. So that's why they're intermediates. Okay, so we need to get rid of the A3 from this expression, and from our pre-equilibrium approximation, it looks pretty easy to get rid of it using this one. So we solve this for A3. So concentration of A3 equals K2 over K minus 2 times concentration of A2 times concentration of A. We can plug that into our overall rate expression so that we have our overall equals K2, K3 over K minus 2, concentration A2, concentration A, concentration B. Okay. We now have A2 in this, but we can get rid of the A2 by looking at our other pre-equilibrium approximation line here. So we solve this for A2, and we find that concentration of A2 equals K1 over K minus 1 times concentration of A squared. Plug that in here, and we get that our overall equals K1, K2, K3 over K minus 1, K minus 2, concentration of A cubed, concentration of B. And so we find that this mechanism predicts an overall reaction rate that is third order in A and first order in B. And it's important to note that that is a different rate law than you would predict from this overall reaction, assuming it's an elementary step. And it's also interesting to note that even though we now have an overall fourth order reaction rate, all of the steps were either unimolecular or bimolecular. Okay. What's the significance of this overall? Like, what does it say about the reaction? So there are two main reasons that we want to know the rate law. One of them is if we are trying to understand the reaction or understand or design a way to have the reaction happen at a speed we want. So two good examples of this. The first one is imagine you are designing you're a chemical engineer and you're designing a reactor where you are trying to get a particular chemical out as a product that you're going to then sell. Understanding the rate law lets you know how changing the concentrations will either speed up or slow down the reaction so that it can happen how you need it to happen. A second example would be if this reaction were something that was happening, say, in the atmosphere, and we're modeling perhaps if one of these things were ozone that we were dealing with, then it might tell us something about how releasing B, in this case, into the atmosphere might interact with the ozone and cause problems with the ozone layer. So basically all of atmospheric chemistry is about kinetics, is about how fast different reactions happen and building up steady state concentrations of ozone or carbon dioxide or anything like this. The other rationale, the other reason to look at reaction mechanisms is because if we have a basic science interest in how a reaction actually happens, then a rate law can tell us if a particular proposed mechanism is plausible or not. So this is something that's particularly important for, say, pharmaceutical applications. If we find that, if we have a hypothesis that some chemical, because it fits into an active site in an enzyme, can have this particular effect in the body, then testing the rate kinetics of the reaction to see if the association with the enzyme gives us the rate law we expect, then that can tell us that we're on the right track in understanding how a particular disease progresses or how a pharmaceutical might have an effect on the body. Okay. If no one has another question, I'd like to see an example of a catalyst and an intermediate. And then does this example encompass the transition state theory problem types we'll see on the exam? And if not, what would one of those look like? Those are some good questions. So a catalyst and an intermediate, that'll be a separate mechanism. So we'll come back to that in a moment. Transition state theory. So the main thing I would think about for transition state theory is, as it relates to mechanisms here, is to look at this thing right here. Notice that we have a bunch of elementary step rate coefficients that are multiplied together. And so we can think of this R overall that we have as having a K overall, where that K overall is just this particular multiplication and division of the rate constants that we have. Well, let's remember what our temperature dependence of a rate coefficient is. It's from the Arrhenius equation. So K is equal to a pre-exponential factor, e to the minus EA over RT. Okay. Well, if we imagine each one of these Ks having this same form, then our K overall is going to be A1, A2, A3 over A minus 1, A minus 2, E to the minus EA1 plus EA2 plus EA3 minus minus 1 minus EA minus 2 all over RT. And so what we can do here is see that the activation energy that we would see, the temperature dependence that we would see for the overall reaction is going to have an activation energy that's just based on the activation energies of the various steps that are involved. And this actually gives us a very interesting result. It doesn't make a lot of physical sense for an elementary reaction to have a negative activation energy, which says that pretty much every elementary step is going to speed up when you increase the temperature. But because some of these are subtracted, the ones that are in the denominator, you could have a multi-step mechanism with an overall apparent negative activation energy if these subtracted ones are larger than the positive ones that you have. And so that could give you an overall reaction that would slow down as you increase the temperature, because the reverse reactions would be speeding up more than the forward reactions would. Does that general concept there make some sense? Yeah. Okay. So, so that's kind of the connection that I would draw between transition state theory and reaction mechanisms, would be to look at activation energies. And the temperature dependence of rates is absolutely critical, because, you know, again, if you're this chemical engineer trying to design a reaction, then if you're in one of these situations, you might realize, oh, I need to lower the temperature to make the reaction go faster, not raise it. And that's really useful information to know. And you can see why based on the mechanism. Okay, any clarifying questions on this connection to transition state theory? All right, so let's do a different mechanism now, one that includes some catalysis. And again, I am making something up, so we'll see how it goes. So let's say that A and B are our primary reactants. It's going to form C, which we'll have as an intermediate. So we have K1, K minus 1. Now we'll say that C runs into a catalyst D to produce another intermediate E, to K minus 2. All right. E then will decay into our product F and regenerate our catalyst D. So in this mechanism, we have A plus B plus C plus D plus E on the left goes to C plus D plus E plus F on the right. C's cancel, D's cancel, E's cancel, and so our overall reaction is A plus B goes to F. Okay. And so the various components that we got rid of from this overall reaction are C, D, and E. Now notice that C is produced by an early step and consumed by a later step, so that is an intermediate. E is produced by an early step and destroyed by a later step, so E is an intermediate. But D needs to be there for the reaction to proceed and is regenerated at the end. So D is a catalyst. Okay. So This particular reaction that we have listed here is another one that I've set up so that we could do this via the pre-equilibrium approximation, because we have this step is an equilibrium, this step is an equilibrium, and let's assume that this step is the rate limiting step. So why don't we have you guys do that right now? So. Will this setup be the same as the exam? It'll be something like this, yeah. Probably what I will do is I will provide you with a couple of different proposed mechanisms for the same overall reaction, have you determine the rate laws for each of the two, and then compare them and see how could you tell the difference experimentally between the two to see which mechanism is right compared to the other. So go ahead and take a shot at this one. Okay. People ready to see the results, or do you want some more time? Okay. All right. So I did the pre-equilibrium approximation here for the first equilibrium. Knowing that C was an intermediate, I went ahead and solved for C. I did the pre-equilibrium expression for the second equilibrium, and knowing that E was the intermediate, I solved for E. And then I went ahead and plugged in the C expression here so that I have E in terms of the two reactants in the catalyst. And then I took the overall rate expression and just plugged in what I had found for E into this to get a rate law that only depends on the reactants and the catalyst. And so we find in this case that it is first order in each of the reactants and in the catalyst. Can you explain the last two steps so I can understand, verify my understanding? Okay, so he- looking ahead, I had known this part right here. So I knew we wanted to have E in terms of just A, B, and D. So having these two expressions here, I plugged our expression for C into this so that I have an expression for E only in terms of these. And then this just gets plugged into the overall rate because we had been told that this step was rate limiting. We know that K3 times E is our overall rate. So then I can plug this in for E to get the overall rate. Why is E the final equation that we are looking for? So it's because if we look at this as rate limiting, we can jump immediately to overall equals K3 times concentration of E. Okay. And we keep D because it's part of the rate limiting step. So we keep D because it is a catalyst. There wouldn't be a way for us to get rid of D. We see that it is a component that is necessary for the reaction to happen. And in fact, when you're doing this analysis, one of the things some people will do is write a D over the arrow saying that this reaction only really goes in the presence of this other thing D. It's not a reactant, it's not a product, but it's necessary for it to be there. Now, the problem is that we keep putting different things on top of the arrows. So we sometimes use the rate coefficients over them. If we're doing thermodynamics, we'll put delta H's over it. Here I'm saying put catalysts over it. If it requires heat for it to happen, you'll sometimes put a delta over it for some reason. So there are all kinds of things you put over the arrow. But if you want to keep track of what's the catalyst, this is one way to do it. And so the question here is, does the overall always mean rate limiting? So there are several ways to determine what the overall rate would be. If you are told that a step is rate limiting, then yes, then you use that. If you are not told that a step is going to be rate limiting, then what you might want to do is look at the overall reaction, see that the product is F, and so then whichever step produces F is the one that's going to be the one making products, and so we'll call that the overall rate. So there are different ways you can go about go about determining which reaction to start with based on what information you're given. So what we crossed out at the beginning doesn't really tell us much about what we need at the end, right? So it does tell us what the set of non-reactants and non-products is. And, but you have to look a bit closer to figure out, is it an intermediate, is it a catalyst, or maybe even, is it an inhibitor? It's possible for something to act kind of like a catalyst, but instead of speeding up the reaction, it slows down the reaction. And so catalysts and inhibitors can be part of the final rate law, but intermediates cannot be. How would we tell an inhibitor from looking at it versus a catalyst? You know, just looking at it, it's kind of hard sometimes, but I can give you an example. And this is a real example from biochemistry. So suppose we have an enzyme, so E stands for enzyme, that reacts with a substrate, meaning the thing the enzyme acts on. So it might be a protein, it might be DNA, it might be any number of things. It goes together to form an enzyme substrate complex. This is an equilibrium. And then the enzyme substrate complex goes on to form an enzyme product complex. And then the enzyme product complex separates to regenerate the enzyme, and the product goes away, and now the enzyme can come back and recatalyze the reaction. Well, what if we have an enzyme plus an inhibitor, which goes together to form an enzyme inhibitor complex? And the inhibitor doesn't go off and cause a cause product to be formed. It doesn't change or anything. All it's doing is tying up some of the enzyme so that it's not available to go through this reaction right here. So what would happen if you did a rate analysis on this kind of mechanism is you would find that the inhibitor would have a negative reaction order. Just by looking at the steps themselves, it's not always clear what that something would be an inhibitor versus a catalyst. I mean, and if you look at it and see, okay, this seems to be taking one of the reactants I need and sending it down this path that doesn't seem to ever lead to what I need, then that would make you start thinking, okay, probably it's an inhibitor. But once you get past, I mean, this is a mechanism here with 2, 3, 4, 5, 6 steps. Once you get too much past about 6 steps, that's a lot to keep in mind at once. So, so I wouldn't expect you to just look at the mechanism and immediately say, yeah, that's an inhibitor. All right, we've got about 3 or 4 more minutes. Anything else we can chat about? Yes?
So in the video we made of example problem, when you did the method of flooding, you changed the A concentration really low,
Mm-hmm.
and then changed the B concentration just a little bit. So that's the question. So why didn't you change C at all? And like what made you decide to change it to the shortening method?
Okay, so for the method of flooding, so that chat can hear the question. In the video where I was going through using the spreadsheet, when I was doing the method of flooding, I changed the concentration of A to be very low, and then I changed the concentrations of B to be some different amounts that were still much larger than A. And then I didn't change C at all. And so then why was I approaching it that way? So generally, you want to, whichever species you are monitoring. So noticed in that video, A was the thing we were watching the disappearance of, right? So whichever one you are monitoring, you want to have the very low concentration because you want to be able to see it go from its initial concentration down as it approaches 0, as it reacts away. If you had chosen to monitor B and had done the same concentrations I did, where B was much more concentrated than A, then it would be at its initial concentration, and then at the end of the reaction, it would still pretty much be at the same place. It would have gone down a little bit, but not much at all. So you wouldn't be able to do much with that information. So whichever species you are monitoring is the one you want to have a low concentration of. Now, in the method of flooding, remember that what we are doing is saying that our overall rate is going to be some rate coefficient, A to some power, B to some power, maybe C to some power. And then what you do is you say, if I make this one really small compared to these, then by the end of the reaction, these will not have changed much. So I can fold a bunch of these things together so that K, B to the B, C to the C in one particular reaction is going to be essentially a constant. And we can treat the rate law, therefore, as K observed, A to the A. And you remember at the beginning of the class, I said that doing the graphical analysis to see which type of plot is a straight line only works if you only have one species that changes. Well, we've just created a situation where only one species is changing because the B and the C are so large in concentration that they're not changing much. All right. Now, once we do this and we see, okay, the natural log plot versus time was the one that gave me a straight line, we know that this is a 1 and it's first order in A. And the slope gives us negative k observed, right? So this is the negative slope of that curve. So now what you can do is then plot your k observed versus a changing concentration of B. It's still big, it's still flooded with B, but we're now changing how much it's flooded with. So if A is down at like 0.001 and B is at 1 molar, then we do, and then we're going to find some value at 1 molar of K observed. Now let's change B to 1.2. Well, now we're going to get a different K observed, might be up here. Now do 1.4, another one up here, and so on. And then you look at this shape, and hey, if you get a straight line, then that means that it's varying linearly with B. So this would have to be a 1 right there. If instead you do it and you get a point here, and a point there, and a point here, and it starts to look maybe quadratic or something like that, then you start doing some tests to see, okay, what's it looking like? So if you could then plot like the square root of K observed, which would get rid of that square that you have in the B, and see, do you get a straight line then? And if it is, then you know, yeah, okay, it's squared, so we have a second order in B. Something like that. Does that make some sense? Okay. All right, well, we are pretty much out of time for today. So thank you all. Some very good questions. Yeah.